Yeah, thank you for the organizers, and thank you for coming. My talk is based on joint work with a number of people over the years: Henry Cohn, Jim Propp, Andrei Okunkov, Scott Sheffield, Jan de Heer, Sam Watson, and many other people. It's something I've been working on for a long time, maybe 20 years, and I know it's a kind of diverse audience, so if you have any questions, feel free to interrupt. You know, I've been doing it so long that I've sort of forgotten what's non-obvious and what's obvious, so don't be shy. I've been teaching, last semester I taught complex analysis, undergrad complex analysis, and one thing that mathematicians appreciate is that you know, the general public doesn't, is the notion of an analytic function, right? Analytic function is something which you don't really find in nature. And you know, when you teach this notion of complex analytic function, you know, it takes a long time for the students to, you know, come to appreciate what kind of object that is. And if you try to find an analytic function in nature, well, I don't know really where to look, but the one place you can find it is a soap film, minimal surface. You know, there's some version of an analytic, and in fact, as we all know, one can parameterize soap films by analytic functions. In this case, you take your two favorite analytic functions, f of z, g of z. You plug in this, do these integrals, plug in, and these are the x, y, and z coordinate of some surface in R3, which will give you a minimal surface. Right, so there's this very simple, you know, real object. The soap film, you know, is very easy to make. You dip it into your soap film, and it just appears magically. But underlying that is actually quite sophisticated mathematics. And so I think that's a good place to sort of visualize what an analytic function is, right? If I, you know, you can sort of imagine that if I sort of knew a soap film very well, near one point I could sort of, you know, do the analytic continuation and get it everywhere. Right, so that's the Weierstrass Enneper parameterization, which hopefully we all know. So I'm going to talk about a different kind of minimal surface now, one which came up in a completely different context, probability context. But here's an example. So it's still going to be a surface, a two-dimensional surface in R3, but now it's a piecewise linear surface. So you take the cubic lattice, Z3, and you look at all the unit squares from the cubic lattice, and you make a surface, PL surface, out of those squares. Right? So you're just gluing the squares along the, you know, you're not allowed to translate the squares. You just make a surface which sits inside the cubic lattice. This is called so you can think of this as in what sense is it a minimal surface? Well, if you think of the boundary here as some sort of wire frame, three-dimensional wire frame, and I want to span that wire frame with a surface where all the faces are unit squares from the cubic lattice. Well, this is the smallest area you can achieve is, well, you know, you have to fill in the whole thing. The area is, of course, I guess 3n squared, right? If it's an n by n squared, right? You need 3n squared faces, and well, of course, but the problem is there are many different solutions. Of course, there's a huge number of different solutions. I can sort of do the lowest possible one is like the empty box, or I can have the full box, or any of these surfaces in between. And so, unlike the previous case, the soap film, in this case there are many solutions. How do we make sense? How do we make sense of this as a minimal surface? Well, as from a probability point of view, we can think about a random such object. There's a natural measure on the space of surface. There's a finite number of surfaces. We can just take the uniform measure. That is, give them all equal weight and pick one at random. And here, let me show you a simulation. So here's, just so you can see the sort of the three-dimensional, can everybody see that? I don't know if you can see the detail from the back row, but here's a three-dimensional picture of a randomly chosen minimal surface among all possible stepped surfaces spanning that particular wireframe boundary. And what you can see is that if you squint your eyes, it looks kind of smooth with some fluctuations. And this limit shape phenomenon is the phenomenon by which, even though there are many, many random surfaces spanning this frame, a typical, almost all of them lie near a particular fixed non-random surface. That's what I mean by this limit shape. So when we think about this as a probability model, we're kind of in trouble because when you learn probability, you learn about probability in one dimension, right, or two dimensions, or maybe three dimensions if you're feeling bold. But this is not a small dimensional problem. It's really a random object. It's a random surface, and so it's a sort of an object. It's a random measure in some infinite dimensional space. Yes.
Yeah, your surface is also goes up, steps up. It never comes down.
Yeah. In this particular case, if I have a minimal surface spanning this thing, it never folds over itself, or it always is going to project monotonically to this plane, the 1, plane. So it's going to be a monotone object. In fact, in this talk, all of my surfaces are monotone in this sense, step surfaces in this sense. So if you like, I can describe this as a graph of a function on the x plus y plus z equals 0 plane. Okay. Okay. So our classical probability methods don't really work in this setting because we have an infinite dimensional space of possible surfaces, at least if you think about such a large such object. And measures in infinite dimensions are, of course, complicated. But we're saved in some sense by this limit shape phenomenon, which I want to explain now in a oops, wrong way. By going down one dimension. So I'm going to do a one-dimension smaller example to sort of illustrate this notion of limit shape, and then you will sort of be able to interpolate that up back to the dimension that I care about, this two-dimensional surface. So let me talk about a random partition. It's a very simple object. You take an integer n. A partition of n is just a way to write n as a sum of smaller numbers. Like the integer 4 has 5 different partitions. Right? You can write 4 as 3 plus 1 or 2 plus 2 and so on. Those are partitions, and associated to a partition is a picture of the partition, the graph. I mean, it's a set of, if you like, it's just a set of boxes that you put in a quadrant, right? Where the height of the boxes are the various pieces of the partition. So this is a partition of 12, 4 plus 3 plus 3 plus 1 plus 1, right? That's called the Young diagram of the partition, drawn in the French orientation. Okay. There's 3 ways to draw a Young diagram: the French, the American, and the Russian. Okay, but this is the French orientation, and but let's now think about a partition of a larger number, like 200. And again, there's a finite number of partitions, but I'm going to pick one uniformly at random. So just do the most naive thing: pick one at random. There it is. That's what it looks like, random partition of 200. And here's a random partition of 2000, same thing. 2000 is, of course, larger, but I had to scale this picture down so that let's scale the picture so that the area under the graph is 1 or something. And if you're sitting in the back row, you probably can't tell much difference between these two pictures. And that's because, there's actually some limiting procedure by which, if I take a large uniform random partition, it has a limit shape. It has a particular shape which it will converge to. In fact, that is the limit shape. This was, I'm not sure the exact date here, but Vershik and Karoff discovered this limit shape for a large random partition, and it has a very simple formula, right? This curve here, e to the minus x plus e to the minus y equals 1, well, I mean, I should scale it by something. This one has area pi squared over 6, but if you want to scale it to have area 1, the formula is a little uglier. So this is the formula which we like. And if you compare that shape there with the shape of the the uniform 2000 partition of 2000, you see that that's actually pretty close. I didn't cheat here. I actually did really pick a uniform random partition of 2000, and you can see that it's following that curve pretty close. And so the theorem is that for any epsilon, if you take the epsilon neighborhood of this Virchow-Kirov curve, then when n is sufficiently large, with probability tending to 1 as n goes to infinity, the scaled random partition will lie within epsilon of that Virchow curve. Okay? That is the limit shape phenomenon. And this, why? So let me briefly tell you why, okay? Because I think this is sort of an important and very simple, it's not really very complicated, but it's an important fact. So what is going on? I'm going to, so our partition is, you can think of our partition as a decreasing function, right? The graph of the partition is just a curve which starts up somewhere up here and ends up somewhere down there. And if I have a particular curve like this one, some random curve, decreasing curve, how many partitions of n, when you rescale appropriately, suppose the curve has area 1 underneath it, how many partitions lie near that one? That is within an epsilon neighborhood of this particular curve. So I just take whatever curve I want. Let's try to count the number of partitions which lie near that curve and try to figure out which curve is the best, which curve wins. All right? And if I have a particular curve, how do I count the number of partitions near that one? Well, let me sort of zoom in to a point on that curve. If the curve is smooth, then when I zoom in, it looks roughly straight. And if it looks straight, then a partition looks something like this black line here. The boundary of the partition looks like that. It's just a broken line which has a particular slope. Right? The only relevant information about the curve near this point is the slope of the curve there. And so if I want to approximately count the number of partitions lying near this thing, I need to know for each point along that curve what it's going to be some function of the slope of the curve. And what function of the slope is it? Well, this is something you all know. If I have a fixed slope, like if I want to go from a broken line from 0, 0 to some other point, mn, the number of monotone curves which do that is just a binomial coefficient. Right? The number of lines, in this case, is just n plus n, choose n, right? And when n is large, if this thing is very large, you can approximate the binomial coefficient. Well, what's this called? The top of the binomial coefficient is n, and the bottom is n times the slope, s over s plus 1, where s is the slope in this case. Okay, but here's the point: is that this thing can be well approximated, has an exponential growth rate as n gets large. If you fix the slope and let n be large, it's roughly exponent of n times some function of s, and that function is the entropy function. Okay. Right. So how many curves go from here to here when this is a large rectangle? Well, it just depends on the slope of the diagonal and the size of the rectangle, and it's e to the n times h of s, where s is the slope. H is this Shannon entropy function, which, well, in this particular variable s looks like that. It's a nice, well, concave function. Okay, so the conclusion is that if I want to, let's go back here. If I want to count the number of partitions near this one, I can chop this up into small pieces where it's approximately linear, take the product of all the counts on each piece, and that is an approximation to the total number of partitions near that curve. Okay, so that count, which I won't try to write it down, but the conclusion is that for each curve, you have some growth rate of the number of partitions near there, right? Remember, there's this extra parameter n, which is the mesh, which is, well, 1 over n is the mesh, which is going to 0. So each curve has its own growth rate, and the overwhelming majority of partitions lie near the particular curve, which maximizes that growth rate. The growth, remember, we're not just counting the number of curves, we're counting the number of curves for each epsilon. Epsilon is the mesh of the lattice. And the growth rate is like the speed, the speed at which it grows as epsilon goes to 0. So and it turns out by concavity, there's a unique curve which maximizes that growth rate, and that is the Virchow-Kirov curve. So this curve, that one, is the unique one which maximizes that surface tension integral. The surface tension integral is the integral of the Shannon entropy function h of s, where s is the derivative, right, along the curve. And, well, along the appropriate domain. So this surface tension integral is maximized exactly for this one. So the finding the maximal curve becomes a problem of maximizing some integral. It turns into a variational problem. So our problem now is a variational problem. Okay. Any questions about that? That was the one-dimensional case. So you can imagine the same thing works in 2 dimensions or 3 dimensions. Well, in fact, we can do exactly the same problem, except it's a 3-dimensional partition now, where we have a set of cubes which we stack into a corner of a room, right? N cubes, and we look at all possible ways to stack them so that we always push them to the back so that it makes a nice monotone surface. And as n gets large, it again converges to some limit shape, right? That limit shape was computed. Well, we computed it with Raphael Serf in 2001, and roughly the same time, Okunkov and Rashtikin computed this. But later on, we discovered that it had been computed back in the 80s by physicist Nienhuis. But there is some nice limit shape there. Oh, I have a picture of that limit shape. Something interesting, where is it? Here. Something interesting happens about this in this limit shape. You solve the appropriate variational problem, and you find this nice analytic function here, but it doesn't extend over the whole plane. It has this boundary here, well, this free bound. Sorry about the jaggedness. It's just a computer, but it's got these facets. Outside here, there are no boxes. All the boxes lie in this region here. So but the limit shape is actually smooth. It's C1 at least across this boundary. So there's a facet here, which is just the axis plane, and then this part is analytic. And then there's another facet here. So it's C1 but not C2 across this boundary. It's kind of an interesting phenomenon by which you start with this very natural variational problem, and it leads to this non-analytic behavior. I can rotate that around, but I don't know if that helps. Okay.
So is that expression the formula for the surface in dimension 1 you wrote down?
Yeah. Ask me afterwards. The formula is a little bit too complicated to display here, but I can explain. Well, here's at least the limit shape theorem, right? Which I gave you the sort of the one-dimensional version here, and this was the theorem of Henry Cohn, Jim Propp, and myself. in 2000, so 18 years ago. So if I want to describe, so here's the setup. We have the same setup. We have some wireframe in R3, and we look at this minimal surface, this sort of piecewise linear minimal surface which spans that frame. And now we're going to let the lattice spacing tend to 0. So we fix the wireframe, but we're going to let the lattice spacing tend to 0 so that the little squares get smaller and smaller. And then we can describe our limit shape as the graph of a certain function h. Just for convenience, I describe it as a graph of a function h from the region in the plane here. Think of the blackboard, this polygon as some region in the plane, in the x plus y plus z equals 0 plane, and I describe the shape as a graph of a function h from the plane to R. And the function which you get in the limit is the unique minimizer of a certain surface tension integral. Right? Now, again, the surface tension here only depends on the slope, the normal vector, if you like, to the surface. And I'll tell you what the formula is for sigma in a second, but you integrate over the surface some surface tension as a function of the slope, times the area measure. And then you minimize it for all possible h with the correct boundary conditions. Right? It's just like the soap film problem, except for a soap film, I would be using the surface tension, which is the area of the graph of the surface. Right? Here it's a different function. It's not just the area of the graph. It's a completely different function. And I want to tell you what that function is. That the function is somehow important. The particular form of that function is very interesting. And right, in the one-dimensional case, the function was this entropy function, which is a very familiar function, the Shannon entropy. It's a less familiar function in 2 dimensions, but that's sort of the key to understanding everything about it. So again, for each slope of surface, right, there's some growth rate. If I take my step surface and I constrain it to have a particular slope, like in other words, if I think about it I can also think about it as a tiling problem with blue tiles, green tiles, and red tiles, and I have to fit those tiles together. And if I've got many more red tiles than greens and blues, then the slope will be tilted in the direction of red. So if I let S be the density of green tiles and T be the density of blue tiles, then the surface tension which I'm looking for, which is just the exponential growth rate of the number of configurations, is going to be some function of S and T. And the number of surfaces or the number of tilings of a given region is just going to be exponential of the area of the region times that. That's sort of the definition. This is the definition of the surface tension. Okay. In one dimension is the entropy. What is this magic function sigma? Well, there's a plot of sigma. The sigma is, the densities S and T vary between 0 and 1, and their sum is less than 1. So the domain of sigma is this triangle, the unit triangle in the plane. And sigma is this nice convex function here, which is 0 on the boundary and has a unique minimizer at the center of the triangle, 1/3, 1/3, 1/3, because that's sort of the point of maximal symmetry, is where you have equal number of tiles of each type. I could just sort of brutally give you the formula for sigma, but the formula by itself is not very meaningful. So let me try to explain something interesting about it. There's a different way to parameterize the space of slopes, right? So I can the space of measures. Let me see. There's 2 ways to sort of to make such a picture, right? If I want to find a configuration with a particular slope, I can just fix the density of green tiles and the density of blue tiles and the density of red tiles, which is 1 minus S minus T. Alternatively, I can change the measure, change the underlying measure away from the uniform measure. If I give the green tiles if I give each tile a weight depending on its color, like the green tiles get a weight, something e to the x, blue tiles get a weight e to the y, the red tiles get weight e to the z, or 1 if I scale, then I can, the weights play a role of changing the measure so that red tiles if red tiles have a large weight, then that configuration will have a higher probability. So the weight is going to be proportional to the probability is going to be proportional to the product of the weights of the tiles. So the point is that now instead of sort of fixing the densities ahead of time, I can fix the weights, and the weights will determine the densities. It's kind of like when I make a I mean, the analog in one dimension is making one of these broken lines where I use a coin. I can use a biased coin. If I have a coin which comes up heads with probability p and tails with probability 1 minus p, then the slope will be some function of p. It won't be exactly p, but it'll be some function of p. That's kind of the analog here, where each red tile has a weight, green tile has a weight, blue tile has a weight, and I give a weight to the configuration, which is the product of the weights of the tiles, and that will bias the tiles with the configurations with a particular slope. And so it turns out that there's a nice, for every x and y, there's an s and t, and vice versa. There's a bijection. So x and y parameterize the same space of slopes. But the map, which gives you the slopes as a function of x and y, that's a non-trivial map. In one dimension, it's sort of just a linear map. If I tell you the bias of the coin, you can compute the slope. It's very easy. But here, if I tell you the weight, how do you get the slope? That's pretty non-trivial. And here's the answer. But the answer is quite mysterious and beautiful. And here's the answer. So you take a Euclidean triangle. I'm going to put one vertex at 0, one vertex at 1, and let's put the upper vertex in the upper half plane at z, complex number z. And now, if I let pi s and pi t be the angles of those two edges, then this edge has length e to the x, and that edge has length e to the y. This triangle describes the relationship between the weights and the angles, the weights and the densities. All right, that's a beautiful and mysterious relationship, which I can't explain why that's true without going through a long calculation. I don't have a short explanation for that, but it's true. You can believe me. And one thing you can discover from this relationship is that if I think of x and y now as functions of s and t, right? If you give me an s and t, I can fix that. I can make a triangle as long as s plus t is less than 1, and that will determine x and y. So x and y are functions of s and t, and turns out, also mysterious fact, that dx dt is equal to dy ds. Weird. But that means that there is you can make this closed form x ds plus y dt, and its integral is this function sigma. So sigma has this property that the dds of sigma equals x and ddt of sigma equals y. Okay. So this is a way to write down the formula for that surface tension function here. Right? That's the surface tension function, and it has that property. It's defined by these equations. Right? If you want, you can write down some trigonometric formulas for x in terms of s and t. There's a little bit of trigonometry. You can do that. You can do the integrals and get an exact formula for sigma, and it turns out to be a nice function, which number theorists know. It's called the Bloch-Wigner dilogarithm. If you write sigma in terms of this variable z here, it's the Bloch-Wigner dilogarithm z. So arg of 1 minus z log absolute value z plus the imaginary part of the dilogarithm of z. those of you who know some hyperbolic geometry might recognize this as a volume of a certain ideal three-dimensional simplex. Okay. Okay, moving on. I keep going the wrong way. I said that there's this underlying calculation which you can do to arrive at that formula for sigma. And there's a little bit of combinatorics, which let me just sort of, how are we doing on time? Lost my clock. Okay, I think we're okay on time. Any questions so far? Underlying this model is a simple combinatorial model, the model of perfect matchings of a graph. Right? If I have this, see the black graph, the honeycomb graph here? It's just a graph with, a planar graph with hexagons, regular hexagonal tiling of the plane. I took a piece of that. And a perfect matching of a graph is just a way to pair up neighboring vertices. So you select a set of edges such that which pairs the vertices, each vertex paired to a neighbor, like in black there. And every time you have a perfect matching, you can, in the dual graph, you have this sort of rhombus tiling, which is one of my stepped surfaces. So the green object is the stepped surface associated to a perfect matching or a dimer cover of that black graph. And there's a theorem, 50 years old, Castellan's theorem, tells you how to count the number of perfect matchings of a planar graph. And the result is very simple in this particular setting. All right, if you have a graph inside the honeycomb graph, like this black graph here, and you want to count the number of perfect matchings, you just take the adjacency matrix of the graph. So it's a matrix indexed by the vertices with ones and zeros, depending on whether they're adjacent or not, right? And then the number of dimer covers, the number of perfect matchings, is just the square root of the determinant of the matrix. Okay, very beautiful, simple result. This combinatorial fact is what allows us to get all those formulas, right? If I have a big region, I want to count the number of configurations or compute the exponential growth rate. This theorem turns it into a linear algebra problem. I have to compute some determinant of the adjacency matrix of the underlying graph. That's why we can do all these calculations. In this particular case, right, I've got 24 vertices for this black graph. So it's a 24 by 24 matrix, and the determinant is 400. I did that on the computer. I didn't do that by hand, but the square root is 20, so there's 20 possible perfect matchings of that graph. Okay, very simple. The proof of this theorem is also very simple. It's one slide long, okay? Do you guys want to see the proof? Okay, yay. Well, the graph is bipartite. It's got, you can color the vertices white and black, so that whites are only adjacent to black vertices. So the adjacency matrix of the graph, if you put all the blacks first and then all the whites, it has this form. And so really, the square root of the determinant of K is just the determinant of this matrix A. Right? If the graph has any perfect matchings, it's got the same number of black vertices as white vertices. So A has to be a square matrix. And if I expand, A is just the adjacency matrix from whites to blacks, if you like. A is indexed, rows of A index white vertices, or black vertices, and columns of A index white vertices. So the determinant of A just expanded over this metric group. What's that expansion called? Laplace expansion, or I don't know. Anyway, expanded over this metric group, and look at all the terms. Each term here is 1 or 0, and the term is going to be 1 if and only if, vertex B1 is adjacent to vertex W sub sigma 1, vertex B2 is adjacent to vertex W sigma 2, and so on. So the non-zero terms in this expansion correspond to exactly ways to pair up the black vertices with neighboring white vertices. Those are perfect matchings. The only thing you have to worry about is the signature, the sign, because this part is correct. It's 1 if and only if you have a perfect matching. Otherwise, it's 0. So we're counting the correct things. We only have to worry about whether the signs are all the same or, well, we have to show that all the signs are the same so that it's a sort of a coherent sum. There's no cancellation because we want to count each perfect matching with the sign plus 1. Right, so the sum has one non-zero term for each dimer cover. All the other terms are 0. So how do we compare signs for different perfect matchings? Well, here's the thing. Suppose I have two matchings which differ just on a single around a single hexagon. Right, I have some big space and big matching, and suppose these two matchings differ just on a single hexagon. This hexagon has these 3 matchings and these 3 edges in the matching, and this one has those 3 edges. I flipped these 3 to those 3. Well, what happens is that the signature of whatever the signature of this permutation is here, it's the signature of this permutation multiplied by a 3 cycle. But a 3 cycle has positive signature, so these signatures are the same. So if two matchings differ on a single flip, then they have the same contribution to the determinant. But now you just have to see that, any two matchings can be moved from one to the other by doing these flips, because each flip corresponds to exactly to adding a cube on the surface. Right? Imagine, this surface is spanned by these the squares. If I just add a cube to the surface, I push the back side of the cube to the front side of the cube, I move from this matching to that matching. And if I have any two surfaces spanning the same wire frame, I can always go from one to the other by adding cubes, pushing the surface across these cubes one at a time. So that's the end of the proof. Now we can get from one dimer cover to any other dimer cover using these local moves. Okay? All right. Anyway, okay, so let's go on. It's not the end of the story. We still want to say something about these surfaces, and the Euler-Lagrange equation for that surface tension function is kind of scary, right? It's a nonlinear PDE. Wait. I got two copies of the same slide. Sorry. It's a nonlinear PDE. Right? This is the Euler-Lagrange equation which you need to solve. And remember, sigma is this kind of complicated function. But we took a tip from minimal surfaces, and you look at the Gauss map. You look at the equation for the Gauss map instead, right? Which is remember, there's this. Oh, let me go back. You see, remember that instead of parameterizing in terms of S and T, we can use this complex parameter Z. And that is the key to solving this equation. Oh, I keep going backwards. Here it is. If you reparameterize things in terms of Z, so you find this function Z such that the gradient looks like this, you rewrite the PDE in terms of Z, and it simplifies beautifully. Here it is, Zx over Z minus Zy over 1 minus Z equals 0. This is some version of the complex Burger's equation. This is an equation which you can solve using elementary PDE techniques. It's just complex characteristics, called complex characteristics. You can solve that equation, and you find that for any solution, there's an analytic function Q, Q of Z. So if you write this equation, x plus z times y equals Q of z, you can think of this as an implicit function for z as a function of x and y. So you take your favorite analytic function Q. Can everybody see? You take whatever analytic function Q you want, you write down this equation, think about this as z as a function of x and y. Right? Z is complex, x and y are just the x and y coordinates of your in the region you care about. And this will satisfy that equation. And so you can parameterize solutions to this variational problem with analytic functions Q, just like in the Weierstrass parameterization of minimal surfaces. So that was really a surprise. I mean, there's, like 4 years between us writing down this thing and discovering that we could actually parameterize solutions with analytic functions. And it's actually even simpler. The equation is even simpler than the minimal surface equation. It's in fact, I mean, if you write it in terms of if you invert the equation, if you think about the equation as an equation for x and y in terms of z, it's actually a linear equation, which I'm still trying to understand. But okay, so that allows us to, explicitly, solve the equation for some nice boundary conditions like these. Okay, this is not so important, but we can find explicit solutions to that equation. In fact, on the very first slide, sorry, I'm going to go back here. See, for this particular shape, right? See this? See that curve there? Turns out that, like in the three-dimensional partition, the limit shape here is piecewise analytic. It's got near the corners, it's got these facets where all the surface is just going in the direction of one of the axes planes, like here. But then once you cross this yellow curve, it becomes there's another analytic piece, which is actually curvy analytic piece. And this kind of surprisingly, this yellow curve here is actually an algebraic curve. It's just a cardioid in this particular case. So there's a beautiful combination of algebraic geometry, sort of algebraic geometry in dimension 1. There's algebraic objects and analytic objects inside that arise in this setting. Okay, good. Now, all that was 10 years ago or so. Recently, we started working on a different a generalization of the underlying model, which is what I said before is that the reason that the previous model worked so nicely is because there was this determinantal formula. We could count objects using determinants of the adjacency matrix and so on. But that is a very delicate thing. If you change the definition of the model a little bit, that disappears, and you no longer have those nice combinatorial techniques. But so it's been kind of frustrating that we have this beautiful theory which only works in this very simple case. Well, it's not so simple, but it's in this particular case. So recently we discovered how to generalize it to a slightly more general setting. Not the most general setting we would like, but here we go. It's again a model of stepped surfaces. Again, for some reason I'm not drawing them as stepped surfaces because this is the way people draw them. This is the way physicists have been drawing them for 50 years. But you think about configurations of lattice paths, northeast going lattice paths like this. And instead of using the uniform measure now, we're going to change the measure a little bit by putting in a weight r per corner. So if you like, we take all configurations of this type, and we give a weight to a configuration which gives you an e to the x for this type at a vertex, e to the y, e to the x plus y over 2 times r for the corners. So if you like, you could just think of x and y as, ignore the x and y's, make them 0, and then what you get is a factor of r per corner. And so here, right, a configuration has a probability which is proportional to, e to the vx plus hy, where v and h are the number of corners of number of vertical edges, where here, I said it here. V is the number of vertical edges, h is the number of horizontal edges, and r is the number of corners. So I moved away from the uniform measure, but only in a very, in a reasonably simple way. I'm counting, for each corner I get a factor of r. This is called the 5-vertex model, and it's a special case of a more general model called the 6-vertex model, or the square ice model, which was sort of well known in physics or statistical mechanics, so solved in some special case by Lieb in 69. So what is the 6-vertex model and what does it have to do with ice? Well, the 6-vertex model, typically, you take the square grid and you put orientations on the edges in such a way that at every vertex you have 2 outgoing arrows and 2 incoming arrows. That's called the ice rule, right? So here's a typical configuration, right? And you see that locally there's 6 possible configurations, right? Because at a vertex, 2 outgoing arrows out of 4. There's 6 possibilities, and you give those. Typically you give these such a configuration. Each local configuration has a weight A1 through A6, which can be arbitrary positive real numbers, and that determines a measure. These numbers determine a measure on the space of configurations. What does it have to do with ice? Well, if you think about at each vertex having an oxygen molecule, water is H2O, right? At each vertex you have an oxygen molecule, and it's bonded to 2 hydrogen molecules, and the arrows, the arrows which are pointing toward that vertex, that's where the hydrogens lie. I don't know if you can see the board, but I can draw a little picture. Right, so if I have so imagine having 1 oxygen at each site, and I want to put the hydrogens along the edges, sort of bonding between 2 oxygens, but they're sort of associated. Each hydrogen is associated to one of the oxygens. Okay, so that's why it's called square ice. It's kind of interesting. Apparently, some physicists recently made square ice between 2 sheets of graphene in the laboratory. So you take 2 sheets of graphene and you put this little, there's this nice sort of square grid in there, and they somehow, it looked amazing to me. But it's one of the models that physicists really enjoy, and has a lot of connections to, in fact, it was one of the inspirations for the notion of quantum groups. There's a lot of integrable systems and quantum groups lying in the background of this model, but has not been solved in the most general case. Lieb computed the partition function, the free energy in the case where A1 equals A2, A3 equals A4, A5 equals A6. The other case where if A1 plus A, there's another subvariety where A1, A2 plus A3, A4 minus A5, A6 equals 0. This is called the free fermion subvariety, where you can solve the model using determinants again. But our model is in neither of these cases. It's a different 5-dimensional subvariety of weights. We would like to solve the complete 6-dimensional case, but still too hard. Nonetheless, let me explain what we got, and I've got a few minutes left. So I'm just going to rush through this. So it's a special case. It's a generalization of the Lagrange model, because you can see these. If you look at these blue-green paths, they make these northeast paths. And here's some simulations just for fun. If R is very large, then each path wants to have lots of corners, so it just zigzags very rapidly with some small deviations. If R is very small, then the paths tend to want to go straight. So there's some interesting sort of phase portrait here. But the end of the story is you go through this longish calculation, which I don't have time for, unfortunately, and you find that the surface tension function can be computed again analytically. There's some explicit formula for the surface tension in this case, which depends on R now. And there's a variational problem just like the previous one. And we want to parameterize our limit shapes where this is the new surface tension function. And the underlying PDE, when you look at the PDE for the Gauss map again, it has a very similar form as before. Zx plus zy times some function equals 0. But now the function is not a complex analytic function anymore. It's just a sort of real analytic function of z. So, I mean, a real analytic function of the real and imaginary parts of z. So, we talked to the PDE people, and nobody was sort of able to say, here's how you parameterize solutions in terms of analytic functions, right? This is sort of slightly more general than the most general case people can solve with complex characteristics. So we were, again, stuck there for a long time. But eventually we were able to integrate, to figure out a parameterization. And let me just sort of display the formula here. Ignore the top part of the slide, but here's x and y. You write y as a function of x, and I wrote everything. Think of u as just the variable z as before. It's just some version of z, and you write y as a function of x, where this is an arbitrary analytic function, or if you like, a harmonic function, and then there's an explicit parameterization of the solutions with analytic functions. Again, it's kind of a miracle. We don't really understand why we can parameterize solutions in such a nice way with analytic functions, but you can, it's reasonably easy to take your favorite analytic function and plug it in and get and find a solution. And here, where is it? Here's an example. I don't have a very complicated example, but you can see. Sorry, that. What are you supposed to see here? Anyway, there's a curvy part, and then there's some facets near the boundary. And the one added feature of this problem, which is different from the previous one, is that the boundary curve here is no longer an algebraic object. It's only sort of piecewise analytic. So unlike the previous case where we had this nice algebraic feature to our limit shapes, here we've only got sort of piecewise analytic boundary. You see four different colors here. Those are the breakpoints of analyticity for the boundary of this curve. It's a nice analytic function inside, it's linear outside, and the boundary curve between the two is a piecewise analytic function. Okay, I will stop. Thank you.